Okay, so there's two tests. This is chi-squared test using contingency tables. And what a contingency table is, it's just kind of a fancy word for matrix. And a matrix is just a table that has rows and columns of numbers, okay? And in fact, these rows and columns of numbers represent frequencies, depending on what we're talking about, okay? So the first test that we're going to do today is the test for independence. The two that we're going to look at today, test for independence and homogeneity of proportions, they're done exactly the same way. The only difference is your HO and H1 is slightly different, okay? So the good news is the HO and H1 for the test for independence is always the same. And it's basically whatever things that we're looking at, their independence versus their dependence. Okay, so that makes your life easy for the HO and H1 because it's always the same for the test for independence. The two things we're looking at, their independence is HO and H1 is their dependence. It's still a chi-squared test. It's still a right tail test, so you put all of alpha in the right tail. The degrees of freedom is a little different. So if you remember, your degrees of freedom for the goodness of fit was k minus 1, which was number of categories minus 1. Okay? So with today's test, the degrees of freedom is r minus 1 times c minus 1. And this is really number of rows minus 1 times the number of columns minus 1, okay? And that's how you're going to get your degrees of freedom. So when you see your matrix or your table, you'll see how many rows you have, you'll see how many columns you have. You'll take the number of rows minus 1 times the number of columns minus 1, and that will be your degrees of freedom for the problem, okay? Let's jump right into an example here. A random sample of 210 people were selected and classified. At alpha equals 0.05, test the claim that jogging and blood pressure are not related. Okay? So here we go. At alpha equals 0.05, test claim jogging and BP, blood pressure, are not related. Okay? And this is our given actual data. So we have blood pressure, low, medium, high, jogger, and non-jogger. So low, medium, high, a jogger, and a non-jogger. And let me fill in the details here. So the first row, it's 34, 57, 21. And the second row, it's 15, 63, 20. Okay? So this is today's test. It's a test for independence. And the test value formula is still the same as before, the summation of the O's and E's, okay? The new thing is, how do we get the E's? That's new. And our degrees of freedom is a little new, okay? So let's go ahead and go through the test. Well, HO and H1, they're independent versus they're dependent. And what are we talking about? Specifically, we're talking about blood pressure and jogging are independent, okay? And then H1 is their dependence. Okay, great. So it's alpha equals 0.05, which is a chi-square distribution. And we're going to go all 0.05 in the right tail. This is always going to be a right tail test. And then I need to use my degrees of freedom now. So how many rows do I have here? 2 rows. So 2 minus 1, which is 1, times, and how many columns do I have? 3, right? And 3 minus 1, which is 2. So 1 times 2 is 2. So my degrees of freedom is 2. Okay, so you need to open up to your chi-square table. Go to 0.05 in the right tail. And go to 2 degrees of freedom. And you should get 5.991. Okay, so make sure you get that number. It's pretty easy to look up because our chi-square distribution is set up for right tail area. And so you just have to make sure you find the correct degrees of freedom. Okay? All right, if you remember from last time, our test value formula, does anybody remember what it was? It's a summation. Anybody remember? The numerator was O minus E, quantity squared, over E. And I put this in brackets because this whole thing is repeated. Okay? And with the goodness of fit tests, we had observed values, and then we had these expected values based on what was hypothesized. Okay? Today, it's a little bit different. With contingency tables or matrices, these are all observed values. So I have 1, 2, 3, 4, 5, 6. These were all observed values. Okay? The expected value, we have to figure out ourselves using a formula. Okay? So we're going to have an expected value for low blood pressure joggers. We're also going to have expected value for medium blood pressure joggers, and so on and so forth. For all 6 of these, we'll have an expected value that we figure out, okay? And that formula is, I'll squeeze it in over here. Here's how you find your expected value. You take the row sum times the column sum and divide it by the grand sum, all right? So row sum, let me make some room, times the column sum divided by the grand sum. Okay? So it's going to be really helpful for you to do these sums. Okay? So let's go ahead and extend this table. Figure out these row sums, extend the table here, figure out these column sums. And we were told there's 210 total people, so our grand total is going to be 210. Okay, so go ahead and add this row up, get that sum there, add this row up, get that sum there, and add these columns up. Because we're going to need that to figure out these expected values. Okay, so according to my math here, the first row adds up to 112. The second row added up to 98. The first column added up to 49. The second column added up to 120. And the third column added up to 41. Okay? And again, the grand sum was 210. So if you want, you can put that here as well, 210. Okay, so we have some work to do. So if I want the expected value for a low blood pressure jogger, what I'm going to have to do is take 112, that row that it's in, the sum of that row, times the column it's in, its sum, so 112 times 49, and divide that by 210, okay? And that will give me the expected value for a low blood pressure jogger, okay? And then I'll just put it in parentheses right here, so I have it next to it, okay? And unfortunately, that comes out to a decimal, so it is 26.13 repeated. So see that you get 26.13 repeated, okay? And then you guys need to go ahead and continue and go to each of these, okay? So now spend about 5 minutes, figure out the expected value for each of these. The expected value for this one's going to be the row it's in, 112, times the column it's in, 120, divided by 210, okay? And I'll do that one for you. I already did it. It comes out to 64. And I'm just putting that in parentheses, so the expected values are in parentheses. Okay, so you go ahead and finish this off. Do this one, this one, this one, and this one. Okay, so spend a few minutes, find the expected value for each of those cells. It's just whatever row it's in, that sum, times whatever column it's in, that sum, divided by 210. This one I got 21.86 repeated. This one I got 22.86 repeated. And this one I got 56. And 19.13 repeated. Okay, so a lot of repeats. But just go through your math and double check that those are the expected values you get. And again, just a reminder, for each one of these, you take whatever row it's in, the total, times whatever column it's in, the total, and divide it by 210. That's how you find the expected value for each cell. Okay? Once you're finished with that, so go ahead and take a couple minutes to try to finish that, then we're ready for the test value. Any questions on these so far? Okay, let's start moving into this guy now. So I'm going to sum up 6 things, okay? I go to the first cell, my observed value is the 34, my expected value is the 26.13 repeated, okay? So I'm going to write 34, the observed, minus the expected, 26.1, let's go 4 decimal places, so 1333, quantity squared, divided by 26.1333. That's my first one. Is everybody with me on that? The observed was 34, the expected was 26.13 repeated. So I have O minus E squared over E. So O is 34, E is this, squared over E. Okay? It's the same test value formula we did last week with the goodness of fits. All right, let's move on to the second one. So I'm in this, the first row, the second cell. So my observed was 57. My expected was 64. Quantity squared over 64. And then another plus sign. Okay? So you guys spend a few minutes, go through each one of these. You should have 6 of these when you're done. For each cell, you have an observed minus expected squared over expected. All right, so it's going to take some room on your paper. I'm going to cheat and put dot, dot, dot. And just do the last cell. 20 minus 19.1333 squared over 19.133. Okay, but you should have 6 of those that you need to fill out. Okay, once you have all of those 6 written down, then obviously you have to go to your calculator and add it all up. If it's 5.991 or greater, then we're going to reject, but if not, we're going to not reject. So add this all up. When I did it before, I got 6.789, so see if you get roughly 6.789. Okay, so go ahead. Spend like 5 minutes or so, however long it takes to put that in your calculator, and see if you get approximately 6.789. Make sure to use the parentheses on the numerator. It's this squared over that plus. You could type it all in one equation if you want, but just make sure you have parentheses in the numerator. using the numerator. Did you guys get approximately 6.789? Yes? Okay, good. And let's finish it off. You should get approximately 6.789. That falls in the rejection region. So step 4, reject HO. So we're rejecting that they're independent. So we're saying that blood pressure and jogging are dependent. Okay? Why else would you jog if it didn't affect your blood pressure? Any questions on that one? It's the same formula. The new stuff today is you have to use row sum times column sum divided by grand total to get each of these expected values. Okay? We're going to do another problem. The next test we have is called homogeneity of proportions, but the way we do it is exactly the same as this test. Okay? The only difference is your HO and H1 is based on proportions as opposed to independence versus dependence. Okay? So let's do one more of these and make sure you understand how to do it. All right, homogeneity of proportions. Okay, the example is an advertising firm has decided to ask 92 customers at each of 3 local shopping malls if they are willing to participate in a survey. The results are shown here. At alpha equals 0.01, test the claim that the proportions of those willing to participate are equal. Okay? So let me give you the actual data. So we have 3 malls. Mall A, Mall B, Mall C. And they asked people if they'd be willing to participate in a survey. So we have people that are willing and not willing. Okay, let me give you the actual numbers. So the first row is 52, 45, 36. And the second row is 40, 47, 56. Okay? And the question was, at alpha equals 0.01, are the proportions of those willing to participate equal? Are proportions of those willing to participate equal? Okay, so let's get this problem started with the homogeneity of proportions model. It's easy. The HO is always P1 equals P2 equals P3 equals however many proportions you have, okay? In this case, we had 3 malls, so there's 3 proportions. So your HO is P1 equals P2 equals P3. That's it, okay? Homogeneity of proportions, your HO is always going to be this proportion equals that proportion for however many proportions you have, okay? The alternative is always going to be at least one is different. At least one differs. So again, the good news for today's material is the HO and H1 is always the same. The bad news is it's a little bit more time intensive in terms of calculating your expected values and then calculating the test value. Okay? All right, great. We're done with step 1. P1 equals P2 equals P3. H1 is at least one's different. Okay, moving on. Critical value. So we have alpha is 0.01. It's a right tail test. So let's put 0.01 in the area here. And again, just like the last problem, my degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So the number of rows is 2, and 2 minus 1 is 1. The number of columns is 3, 3 minus 1 is 2. So again, just like last problem, your degrees of freedom is 2. Okay? So look up in your chi-square distribution table, go to 0.01 area in the right tail, go to 2 degrees of freedom, and you should get your degrees of freedom is 2, so your test value is 9.210. Critical value of 9.210. Okay? And of course, I just looked that up in the book. Make sure you have your degrees of freedom is 2, and alpha is 0.01. Okay, now, I actually have good news on this problem. Can anybody see what the good news is already, potentially? Well, go ahead and do the row sum and column sums, and then hopefully you will see some good news. So the first row total, I get 133. The second row total, I get 143. I get a grand total of 276. But here's the good news. What do all of these add up to? 92. They're all the same, right? 92, 92, and 92. And that's actually really good news for us. Because if all the column totals are the same, then we're really only going to have to worry about 2 expected values. And you'll see that in just 1 second. Okay? All right. So 52 is the observed value for people willing to participate in Mall A. What is the expected value for 52? You're going to do this 133 times 92 divided by 276. Does everybody see that? It's this row total times this column total divided by this grand total. So in your calculator, 133 times 92 divided by 276, and you get 44.3 repeated, right? So 44.3 repeated. Okay, now, if I was finding the expected value for this guy, it's also going to be 133 times 92, right? Because it's the same column total. Does everybody see that? So in fact, these first 3, the whole first row, is all going to have the same expected value. And does everybody see why? Because the row is always 133, and each of these columns is always 92, so it's always going to be the same math. Okay? So 44.3 repeated, and 44.3 repeated. Great. Moving on to the second row, if I wanted the expected value for 40 here, it's going to be 143 times 92 divided by 276. And again, just like the last problem, all of these are going to have the same expected value because it's always 143 and it's always 92, 92, 92. Okay? So in your calculator, do 143 times 92 divided by 276, and you get 47.6 repeated. 47.6 repeated, 47.6 repeated, and 47.6 repeated. Okay, now normally that doesn't happen. You guys got lucky that all of these column totals were the same, so really you only had to do 2 expected values here. Okay? Okay, moving on to our test value formula. Summation, observed minus expected, quantity squared, divided by expected. So just like the last problem, you have 6 terms that you're going to be adding up, and go ahead and fill it in. Okay, so the first one, I'll get you started. It's 52 minus 44.3333 quantity squared divided by 44.3333 And that's the end of the first term. You have 6 of those guys that you have to add up. Okay? And I'm totally going to cheat. I'm just going to put plus dot, 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 dot. And then do the last one. 56 minus 47.6666, quantity squared, divided by 47.6666. So spend 5 minutes and make sure that you get the same test value I got, okay? Please make sure, go through it because you're going to have to do it on the exam. Go through it and make sure you get the same value I got. And what did I get? I got approximately 5.60 when I finished this. So see if you get approximately 5.60. That's your goal. Spend a couple minutes, see if you can get that to come out to 5.60. The formula is observed minus expected squared divided by expected. Don't forget your parentheses in the numerator. You can do it all in one, just make sure you have parentheses and squared for the numerators. And then you can add it all up. Did anybody get about 5.60? Yes, no? A couple of you? Great. So everybody should get approximately 5.60 when you add them all up. And I'm going to finish this problem off. So 5.60 is right here somewhere. It's not in the rejection region. So I move to step 4. Do not reject HO. And remember, in this case, HO was saying all the proportions are the same. Okay? So my statement number 5, the conclusion is there's not enough evidence to suggest that there's a difference in the proportions. Okay? Or, what was the question? Are the proportions of those willing to participate equal? Yes, it appears the proportions of those willing to participate are equal. So the answer to the question is yes, they're equal. Okay? Now, on the exam, how are you going to know it's a homogeneity of proportions versus a test for independence? Well, it'll be clear because they have to give you a matrix with a row and column of numbers. And then what's the question asking? Is it asking for a relation between two variables, independent, dependent, or is it asking about proportions? Okay? So it should be pretty obvious in the problem. Any questions on this? This finishes up our chi-squared test. Okay.